My name is Holly Heat, and I will answer Chapter 17, Question 48 on page 830 in the textbook. The question is, a 100 milliliter buffer solution is 0.175 molar in hypochlorous acid and 0.150 molar in sodium hypochlorite. Part A is asking, what is the initial pH of this solution? The concentration of HClO is 0.175 molar, and the concentration of NaClO is 0.150 molar. We can use these concentrations and plug them in to the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the concentration of base divided by concentration of the acid. To find pKa, we need to take the negative log of the Ka value. The Ka value of HClO is 2.9 times 10 to the negative 8, and once we plug in the concentrations as well as the Ka value, the full equation is pH equals negative log 2.9 times 10 to the negative 8th plus log of 0.150 molar divided by 0.175 molar, and we get a pH of 7.47. Part B is asking, what is the pH after addition of 150 milligrams of hydrobromic acid? The reaction will be H plus ClO minus yields HClO. To determine the number of moles before H plus is added, we need to multiply the molarities of both ClO minus and HClO by the volume of the solution, which is 100 milliliters or 0.1 liters. So once you do that, you will get 0.0150 moles of ClO minus present before H plus is added, and 0.0175 moles of HClO present before H plus is added. To find the number of moles of H plus added, we need to convert 150 milligrams into grams and divide by the molar mass of hydrobromic acid, which is 80.9 grams per mole, and we get that there are 0.00185 moles of H plus added. Since there are less moles of H plus present than there are for ClO minus, that means H plus will be the limiting reagent, and all of the H plus will react with some of the ClO minus to form HClO. To find the number of moles after H plus is added for ClO minus, we need to subtract the number of moles of H plus from the number of moles of ClO minus present, and we get 0.0132 moles of ClO minus. For HClO, we need to add 0.00185 moles to the number of moles of HClO present in the solution already, and we get a total of 0.0194 moles of HClO. Here is a mole table to visualize all of our calculations. To find the new concentrations, we need to divide the number of moles by the volume of the solution, which is 100 milliliters or 0.1 liters. So the new concentration of ClO minus is 0.13 molar, and for the concentration of HClO, it is now 0.194 molar. Using these new concentrations, we can plug them into the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the concentration of the base divided by the concentration of the acid. So our full equation will be pH equals negative log 2.9 times 10 to the negative 8th plus log of 0.132 molar divided by 0.194 molar, and our new pH is 7.37. Part C is asking, what is the pH after addition of 85 milligrams of NaOH? The reaction will be OH minus plus HClO yields ClO minus plus H2O. We already determined the number of moles before OH minus is added from part B. So for HClO, we have 0.0175 moles, and for ClO minus, we have 0.0150 moles. To determine the number of moles of OH minus added, we need to convert the 85 milligrams into grams and divide by the molar mass of NaOH, which is 40 grams per mole, and we get 0.00213 moles of OH minus added. Since there are less moles of OH minus present than there are for HClO, that means OH minus is the limiting reagent, and so all of the moles of OH minus will react with some of the moles of HClO to form ClO minus and H2O. To determine the number of moles after OH minus is added for HClO, we need to subtract the number of moles of OH minus added from the number of moles of HClO present, and we get 0.0154 moles of HClO left. For ClO minus, we need to add 0.00213 moles to the number of moles of ClO minus present, and we get 0.0171 moles of ClO minus. Here's a mole table to visualize all of our calculations. To calculate the new concentrations, we need to take the new mole values and divide by the volume of the solution, which is 100 milliliters or 0.1 liters. So the new concentration for HClO is 0.154 molar, and for ClO minus, the new concentration is 0.171 molar. Using these new concentration values, we can plug them into the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the concentration of the base divided by the concentration of the acid. So our full equation should be pH equals negative log of 2.9 times 10 to the negative 8th plus log of 0.171 molar divided by 0.154 molar. And our new pH should be 7.58. To summarize, in part A, we used the Henderson-Hasselbalch equation to find the initial pH of the solution, and we got 7.47. In part B, we used a mole table and the Henderson-Hasselbalch equation to find the pH after adding hydrobromic acid, and we got a pH of 7.37. In part C, we used another mole table and the Henderson-Hasselbalch equation to find the pH of the solution after adding NaOH, and we got a new pH of 7.58.